Hi, I'm Matt Calhoun, and I'm going to share a project that I've been working on. Hopefully, you'll find it interesting. As you can see in the title, it's related to getting robots to cooperatively and autonomously perform a search over an area. And so the project uses multiple areas of AI that I'll just mention. Deep neural networks, pretty much every modern AI application uses reinforcement learning, where you set up a system of rewards and an agent or a system tries to train itself to gain the most rewards possible, and you can use it to help things figure out how to do things for themselves. Computer vision, so you can find things on images. Clustering, that's a way of a system being able to find patterns without you necessarily having to tell it exactly what to look for ahead of time. And evolutionary algorithms, which is a way of solving problems that kind of mimics natural selection, but surprisingly works pretty well. Anyways, why I'm doing this? I am getting a master's degree in AI at Maryville University, and I've also been making software for about 30 years, and recently I've become a lot more interested in robotics, and I like how they can be cheap and easy to build and fun to work with. So after I had gained a little more experience working with that, it occurred to me that a lot of the tasks that you can accomplish with one robot should be a lot faster if you could get some robots to work together. So, for instance, if one robot can mow your yard in an hour, then 10 or 15 should be able to do it in a few minutes. Or if one robot can search an area in 15 minutes, three should probably be able to search it in about 5. So for my work, I'm focusing on things that involve performing a task over an area, sort of like the things I just mentioned, or like searching or mowing or painting a wall or things like that. But for my reference application, I'm going to focus on search, because that I can do with just a camera, and it's not dangerous or destructive, hopefully. So one aspect of this project or problem that is unique and makes it a little difficult is the cooperation aspect. So the robots are going to need to be able to work together as efficiently as they can. There already are a lot of examples of robots being pretty efficient, such as vacuum cleaners, and they get really good at covering an area in a short time. The nuance that I'm adding here is I want them to cooperate. So in order for them to be able to cooperate, they need to know what each other are doing and what's already been done, regardless of what task they're trying to perform. And just as an illustration here, on the maze to the left, you can imagine if something was trying to traverse this maze by itself, it doesn't need to pay attention to anything else that's going on, just its own little world. Now on the right, if you had two things traversing the maze, trying to do it as quickly as possible, then they would want to not cover the same ground that the other one did. So they really have to be a little bit smarter. So this is a difficult problem, and in order to solve it, I need to figure out exactly what is it that I'm trying to solve. I talked about doing a search or mowing the yard or things like that, but what I'm really trying to solve is that problem of being able to do something over an area using multiple robots as quickly as possible, as efficiently as possible. So the actual physical task, whether it is a search or mowing or metal detecting or whatever, that's a separate thing that I want to decouple from. And the reason that I want to be decoupled from it is if I solve this problem, then I should be able to plug in different physical tasks without having to rebuild this everything else part. To do that, we kind of have to think of whatever the physical task is. I'm using for now search as a placeholder to this whole thing and just as a reference application, but this is what I'm targeting here, everything else. And that should make what I'm building to be pretty flexible. So in order to solve that problem, I need to, because I mentioned it is a big problem, I need to break it into smaller pieces. So I've decided to break it up in the way that this pyramid shows. So I'm going to have a set of physical problems to solve. And so, for instance, what can these robots do? They need to have some common functionality that I can depend on to be there. And I need to either buy or build robots that have these capabilities. What I want them to be able to do is move. So I'm just choosing forward, backward, rotate, strafe, control their speed. I need to be able to aim where they're looking. And then as far as sensing, I need the robots to be able to have vision, and I need them to at least reasonably be able to estimate how far they've gone, and since I told them to go forward. And also the LiDAR. They need, I would like them, it's not absolutely necessary, but I would like them to have LiDAR so I can estimate distance from any angle. Not have to estimate, to be able to measure. Okay, so the second piece of this pyramid, they need to be aware of their position. They need to be able at any time say, where am I? Where am I looking? So it's kind of like GPS. But I want to be able to use a Cartesian coordinate system because that's more in line with a lot of computer science problems that have already been solved in many ways. So I want to be able to have the position in that way so I can apply different well-known techniques. So the robots need to be able to have a way of, or I need somehow a way to be able to map an area so that I can provide to the robots a map of where they're looking. And I mentioned they need to be able to have live coordinates as well. Okay, so the third piece here, context. In order to be smart, the robots, in order to efficiently travel and cover an area and not backtrack, they need to know what's going on. They need to have somewhat of a memory of where they've been, where they've already searched, where things have been found, and also awareness of the other robots, if there are any. If there are any. It needs to know that as well. Maybe there's not any. It needs to know if there are some, what are they doing, where have they been, what have they found. So all of this is context that the robot needs to have. And finally, a strategy. So the robot needs to be able to pull together all that information that I just mentioned and then use it to decide what it should do. And what should it do that's going to help it achieve its goal of collectively covering an area in it with as minimal travel and minimal time as possible. And these robots each need to be able to decide this independently. There's not going to be some mothership telling them what to do. They need to be able to figure it out for themselves. And so some of the strategies here, that I had to actually make some just to play around. So random searching, that's for this type of thing, that's the first thing someone does just to measure how well their algorithm is doing against some standard. So random searching is pretty bad, though. It's like it says here, it's like monkeys typing on a keyboard and then hoping to end up with some great piece of literature. It might happen. It's going to take a long time. It's probably not going to happen. So a well-designed search algorithm, that's okay, and that's kind of the old-fashioned way of doing it, but it does take a lot of time, and there's always edge cases and lots of code to write and test, and you end up having to maintain some code. Anyway, I just don't want to go there. So finally, the AI trained search algorithm, that's what I want to do. So I would rather the system train itself. Okay, so now that I have spent a lot of time determining the scope that I wanted to solve and how to slice it up, I'm ready to solve it. But I did want to point out, if you're, even though I went through that stuff pretty quickly, if you're trying to solve a problem that is any has any amount of complexity, you need to make sure you're spending plenty of time and setting the scope for yourself and breaking it up into manageable pieces. And a lot of times when you go through that, you'll realize you don't have enough experience with something and you need to gain that before you go past that first step, maybe multiple times. But that's okay. That should not stop you from trying to do something. It's definitely normal to realize you're in uncharted territory and have to kind of wade through the waters a little bit. But you want to do that before you jump in and start building something, or you'll get really frustrated really quickly. Okay, so going through my pyramid here, the first thing, physical. So I needed robots, like I said, with some common functionality that I can depend on to be there. So I built these 3 robots. They all have 330-degree vision, made possible by the servos that you see they're mounted on. These are Pi cameras. Each one has 2 Pi cameras, and they all have LiDAR. This one has LiDAR underneath. You can't really see it, but it's there. The tank is track driven. It's the software that's doing all of the positioning and making decisions. I call that the pilot software. The pilot software is running on NVIDIA Jetson Nano. On the mech car, it's running on a Raspberry Pi CM4. On this observer, it's also running on an NVIDIA Jetson, and this observer actually cannot move. So it's more of a test thing that if I need to do some testing where I factor out any movement, then I will wheel this thing around and turn it, or manually push it around. But it helps me get clean observations of things, so which is why I call it the observer. So the car can strafe and the tank cannot, but other than that, their functionality is pretty much the same. The car has a display on the back that I can look at, and it will show me the live coordinates. The tank does not have that. And just to show you kind of how it moves around, there you see it rotate a little bit. They can both rotate, and so that functionality's common. Go forward and backward, and rotate the cameras as that shows to cover the 330 degrees. It's got a little blind spot behind it, so in order to see directly behind it, it would need to rotate. And here in a second we'll see it strafe, I think. Yeah, there it goes. Nice. Okay. Yeah, so that's the physical. So the next step on the pyramid was the position. So I could not find any indoor cheap positioning systems for robots, so that's it. Thank you. No, I'm just kidding. Actually, I unfortunately had to build one. So, well, actually I like doing it. It was fortunate. So I made a positioning system where, based on vision, just using those Pi cameras, a robot can capture images and know where, well, I'll run that image through some TensorFlow TF Lite models that I created, and I have landmarks. So I've created this concept of landmarks where I bought some items at Hobby Lobby, and I bought a whole bunch of infrared lights, and I can place them at various places wherever I want in the basement and or wherever I am. And I created a map file that's a JSON format. Basically, I can say at coordinate, 100, -50, you will find a cat tree or a house or this light pattern. And for the lights, I came up with this concept of the lights being in patterns. So I can have, like, depending on whether the light is making a triangle pointed to the left, a triangle pointed to the right, a vertical line, a square, those are all different landmarks. So I have a map tells the robot where everything is. So in my basement or any other area, I imagine if there's a grid overlaid on it, and I choose an origin and I choose an orientation, where's the y-axis and the x-axis. And from there, I measure out where I've placed all the landmarks, and I put that into a JSON file. And so from there, the robot can look around, do some calculations, and pretty much figure out where it is and where it's facing using triangulation. And so this is just to give you an example, some of the angles that are involved in that triangulation. If possible, so it generally estimates the distance using calculation of the camera's field of view and the known height of the object and how high it appears on pixels on the image. But that's an estimate. So anyway, if you looking at these, and if you know a little bit about trigonometry, which I claim to only know a little bit myself, you can imagine that you should be able to figure out where you are by doing some triangulation. So the only problem with that is, and it's a big one, that this vision-based distance, it does work pretty well, especially with a system of lights, but sometimes the bounding boxes that come back from TensorFlow around an object are not quite right. So if I'm using the height from top to bottom of this to estimate the distance, sometimes it can be off. So a couple of ways I deal with that is, for one, I have the onboard LiDAR, and I will try to replace my estimate with a LiDAR measurement, but that is not always possible. Some of these things some of my landmarks don't even show up on LiDAR, even if I tried. The LiDAR just goes under them or over them. So this is where the evolutionary algorithm comes in. What I end up with is kind of estimates, and I have a confidence level that I give to each estimate depending on various things. And the evolutionary algorithm will take a whole bunch of distances and a whole bunch of angles and chug through and come up with its best estimate of coordinates, which turn out to be pretty accurate, usually within a few inches. So it's that was fun to do, but this took a very long time. So anyway, it does work well enough for my purposes so far from my testing. So anyway, back to like the actual problem that I was trying to solve, which was not this. Context. That took months, by the way. So context, the robot needs to know what's going on. So it doesn't need just to know where it is. It needs to know where the other robots are, where they've been. And so they need to be able to communicate somehow. So I have the mech car is pulling around this little Wi-Fi router. And there's probably another way I could do that, but this was easy. So I stuck a Wi-Fi router on the back of there that runs on 5 volts. And that lets the robots communicate their positions and know the positions of the other robots and various information, any of that context that they would need to know. This gives them a way to share that. And I also built an Android app that lets me kind of listen in so I can see all that information visually or as a log of positions and things like that. And I can do other things with it, like send them commands and things. Yeah, so that covers the context. So the final piece of the pyramid was the strategy, which is the most difficult and interesting part. So for that's where I wanted to apply reinforcement learning. I am using a system that's called Stable Baselines 3. Some people forked a other system called Stable Baselines that from OpenAI, who are the people that make ChatGPT. And the Stable Baselines, it's a very neat system that uses PyTorch and your graphics card, and it takes a lot of planning, but you can basically use the Stable Baselines to generate a strategy for you. So you have to put your problems in the right terms for this thing to be able to solve it. And you have to set up a system of rewards, a reward strategy, like I said, that basically rewards your agents. Everything in here is called agents if it's a robot. Instead of robot, we'll use the word agent because that's what they call it. So when an agent does something good, like sees something or goes somewhere and gets closer to something, that's good. And we want to reward that. When it goes out of bounds or runs into something, we don't want to reward that. So by doing that over a long enough period of time, it will learn what's good and what's not. And this is an example of where I was playing around with it, trying to train a thing to walk. This was a nice little simulation. Somebody else made this walker simulation, but I used the Stable Baselines 3 to practice and try and teach this thing to walk. And so you can see at first it's not good. After you've had it training for a while, it'll kind of, it's on its knees or something. But at the end, it's doing pretty well. And the longer that you give it, the better it will get at learning something. So yeah, this is what I want to use to have the robots decide what to do. I don't want to hand code that for them. So the examples that I've worked with and that I've seen of using reinforcement learning to train something show how to train one thing to do something. So, and here's another example that I played around with, which was this moonlander thing. So it's learning how to land on its own, which is great. And that's actually a pretty difficult task. If I tried to do that with the buttons to control it, I would be like this guy over here. But the system learned how to do it pretty well. Now, if you were to throw 2 or 3 moonlanders on here, that would be different. And I've not seen, I'm sure someone's done that. I haven't seen it, but that's more of along the lines of what I'm doing. So I need to have a little bit of a different plan. My plan is first, I'm going to build a simulation that does a good job of simulating what my robots can do, their common functionality of going forward and backward, strafing, looking around, taking pictures, and also the positioning system. Between the robots and the positioning system, there are some quirks where sometimes the robot will need its position, but the vision's getting blocked by something or someone standing in front of it. It needs to be able to react to that. So it's not perfect. It cannot always, or even if it tries to go forward, sometimes it just doesn't go as forward as far as what it meant to. And that all needs to be part of the simulation, those odd situations. So when I have my simulation, I will use this Stable Baselines 3 to train a lone search agent. So there'll be no other agents on the simulation, just the one. And it will learn how to cover an area and search it as quickly as possible by itself. So after I've got that one trained, then I'm kind of in the same position as what you've the best over here. Now I need to add the group aspect to it. So the way that I'm going to do that is, or I'm planning, and I don't know how well it's going to work, but I'm going to basically make a bunch of drones added to the simulation that are following that loner strategy. So they'll each be doing a pretty good job as if they were searching on their own, but they will all be on the simulation at the same time. But they'll be, I will not be training them. They're already trained as well as they're going to get, but they'll just be roaming around doing their thing. So what I will be training then is I'll add another agent that has no idea what it's doing, a blank slate, alongside the loners, and the reinforcement learning system will be training that brand new agent. So it should get good, just like the others, at going around and finding things, but it should not be overlapping what the other agents have done. That's my plan anyway. And I'm not sure how well it's going to work because I've never seen it done, but that's what I'm planning on doing. And I will, once I have that trained, I will kind of throw out those loner agents and make another simulation of just these cooperative agents. And I will visualize a simulation of what they're doing, and I'm going to watch what happens, and hopefully it'll be good. Okay, so the first part of that, I needed to build a simulation. So I did build a simulation. Here's the code. Usually, well, within the simulation itself, there's not much to see other than logs that come out. So this simulation will run. I can tell it how many agents are in it, what strategy they have, and it will basically let them roam around. And again, this is a simulation, it's not real, but it will kind of simulate letting them roam around. And if the agents try to get their position, they have to ask the simulation environment, and it will give them an estimate instead of actually telling them where they are. So there'll be like an error, a little bit of an error in that intentionally, so that they have to learn to react to information that's kind of accurate but not entirely. So I really make this simulation just to copy as much as possible how this stuff really works when it's the real cars. And this can go really fast too. That's the other benefit, is if I try to run things like I have been doing testing with the robots in my basement, it takes forever. But the simulation can obviously go extremely fast. But again, like I said, I can't see anything out of it. And in order for me to make sense of it, I need to be able to visualize what's going on. So I built a visual simulation of it. A way of visualizing the simulation. So on this tool called Mesa that runs on Python, and it's pretty easy to work with, I made a way so that I can display in a browser what's going on in that simulation. So, for example, these green dots are the robots. These blue areas are obstacles. Pool table. Yeah, this is actually my basement. This is a map of my basement, which is generally what my go-to when I've been playing around with this. Especially when you're doing the math, it's a lot easier if I can physically look at something, imagine myself in a certain place, and anyway, that's a lot easier. It makes it a lot easier. But this also is pretty useless for training, because if I were to just use this map and apply reinforcement learning, it would just memorize all the turns, and yeah, that is not useful because they're going to be searching outside of my basement. That's the intention. It just happens to be where I'm sitting and where the weather is nice. So anyway, what I also made a random map generator. So that's what the things will be training on. Every time they start an episode, a search episode, a new random map of a random size within a range will be generated. I've not seen someone randomly alter the size of a map, either for stable baselines. So I don't know what effect that's going to have, but I will find out. So next, the map we just looked at is nice for me to see. It's in a browser, but the agents need their own version to be able to visualize what's going on. In my version, I can see the target. Well, the agents are not allowed to see that until they find it. So I built this rendering functionality that lets the simulation generate image renderings of what's going on in the environment from any agent's perspective. So on this one, there are, I don't know, 4 different simulated agents. The red one is the agent whose point of view was getting rendered right here. So the red is where it is, the green is where it's been. It kind of becomes more opaque the closer it gets to now, and it eventually fades off to nothing. This is the memory. So I'm giving it a memory through this image of where it's been by the fact that it becomes more transparent as we go further into the past. And it also, the other agents show up on here, same thing for them. They become more transparent as we get further into the past until so many steps back we just throw it out. But this is the memory kind of burned onto an image. The yellow area and the light blue area, these are search areas. So this is where these things have searched to help them. It takes into account how far they can usually see and their blind spot. You can see the little wedge back there is the blind spot. And that, again, also fades away with time. So I'm kind of hoping that through reinforcement learning, they will learn to look for white areas that have not been searched, learn how to stay away from the gray areas which are blocked off, and learn how to not run into each other. They get penalized if they get too close to another robot. The diamond is, it's found something. So when an item gets found, when one of the targets gets found and the agent reports it to the simulation, or in a real search it would be reporting it to the other robots that are within communication distance, it shows up on the rendering as a diamond, and other robots should be able to, they all can see that then, no matter which robot found it. So they should all know, well, that's already been found there, so it's probably not likely that I'll find another one right here, but then maybe it is. So I'm not sure what strategy they're going to come up with, but I'm trying to provide all the information. So I also had to create a gymnasium environment that is basically the way that stable baselines can control episodes and of your simulation. So it lets stable baselines run so many steps of your simulation and then reset it. It also, this is where the rewards come in. My gymnasium wrapper looks at the simulation, looks at what an agent has just done, and then determines, do they get a reward or not? How much of a reward do they get? So that's a pretty critical part of getting the system, the training to work right. And then now we get to where I am right now. So my training is actually going on, even though I'm doing this presentation. The training is still in progress for the first agent. It takes a long time. It's from some of the Atari games that you would be trying to train on hardware like what I have, would possibly take a week or more. So I'm expecting probably about the same, and actually my rendering is a little more complex than a lot of the Atari games I've seen, so it might be difficult. I was going to show, yeah, so here it's still running. This is kind of what I get out of it. So it's currently the average, it's 28% done training, and it's averaging about 37 steps per episode. The episode cuts off if it runs into something or runs into a robot. Well, this is a lot better than it was doing. When I first started, it was about like 2 days ago. It was the average episode length was only like 16, and it was getting 0 rewards. Now it's getting some, which means it's seeing things and trying to figure out what to do. So that's where that is. I expect that's probably going to take a couple of weeks. So I just kind of let that thing go, and hopefully it doesn't crash. It's doing pretty well. Been doing pretty well the past few days. So after the training is done, assuming that it is successful, what I will do, all of the decision making I've factored out into a base class that's called agent strategy. And so I can subclass that agent strategy and make new ones, and they kind of just plug in. So then within the simulation, an agent is doing whatever the strategy told it to do. This is my hard-coded reasonable strategy, which if you were to look through here, you'd see basically what it's doing is, does it know its position or not? If it doesn't, it tries to get it. If it's out of bounds, it tries to react to that. It does try to look around for things and take pictures under certain conditions, but this is hard-coded, and this is what I'm trying to get away from. So what I will do is make another version of the agent strategy class that pulls the rendered field just like this does. Actually, this one does pull in the rendered field, but then it doesn't actually do anything with it. So the trained agent is going to pull in that rendered field, which is the image, as a NumPy array. It's going to feed that to the trained model that I get back from Stable Baselines 3. The model should bounce that off of its deep neural network that it's got and come back with an action that I should do. And I will just blindly follow that. That's what my strategy will be. And it should hopefully do pretty well. I don't know. So I will then take that strategy and run it in my simulation with multiple robots, the cooperative one, and I will watch what happens. So again, this is my basement, so sure, I'll see how it does on my basement, but I will also generate random other maps, random numbers of robots, 1, 5, 10, 1 target, 5 targets, whatever. I'll do different variations of this and watch how it goes, and it will be interesting to see how they react to each other. I don't really know what to expect, so we'll see. So anyway, once I've got that done, then the next step is to put them onto the physical robots and run the robots through some tests, and we'll see. Hopefully that goes well. And if so, then what's next? Maybe I will make some treasure hunting robots that do metal detecting on the beach for me while I sit around. I don't know. But anyway, that's the project I've been working on. It's been a lot of fun so far, still in progress, and all the code you can find on my GitHub account. Thanks.